Hi guys, thanks so much for bearing with me with those unanticipated technical difficulties we had. I'm really sorry about that. So I'm going to do this video with you in order to kind of finish up our 2.1 notes, and we'll just continue with 2.2 and 2.3 next class. So we have the trunk circumferences of 40-year-old apple trees in millimeters, and over on our far left, you can see that we have their circumference classes from 69 to 79, 80 to 90, 91 to 101, 102 to 112, 113 to 123, 124 to 134, and 135 to 145. We determined as a class by subtracting consecutive lower class limits that the class width was 11, and this helped us in finding our midpoints and our boundaries. So we've taken the frequency distribution, we've identified the boundaries and midpoints, and now you were asked to find the relative frequency. So to find the relative frequency, what we do is we add up all of the given frequencies, which I'm highlighting in pink right here, and the total is going to be 60. You'll see that 60 is the total of all those frequencies. So for the relative frequency, we're going to take each of our individual class frequencies and we're going to divide them by 60. So first we'll have 2 divided by 60 is 0.033. A good tip is to round decimals to 3 decimal places. So if you convert it to a percentage afterwards, you'll have a whole number point something. So the percent is actually to 1 decimal place. Next, we'll have 3 out of 60, which is 0.05. And you'll see that there are a couple classes that had 3 out of 60, so I'm going to say 0.05 here. At the bottom, the last 2 classes are all 0.05 also, because they were 3 out of 60 as well. So on the left, you see the work. On the right, you see the decimal answer. Back to the third class, we have 8 out of 60, which is going to be 0.133. The fourth class is 19 out of 60, which rounds to 0.317. And then the fifth class is 22 out of 60, which is equal to 0.367. Lastly, we're asked to find the cumulative frequency. For the cumulative frequency, for the first class, it'll be the same as just the regular frequency. But then as we move on to each class, we're going to add up all the previous classes and add it to it. So circumference in our original frequency distribution was what our classes were labeled from circumference. I'm going to label that C. But over here on the right-hand side, I'm going to relabel our classes C, and now I'm going to make them cumulative. So we can see from the left, or the first class said 69 to 79. It's all the numbers that fall before the second class starts at 80. So the first class really represents all numbers less than 80. And the cumulative frequency would be 2. The next class is all numbers C that happen before class 3 starts at 91. So C is less than 91. So I'm going to add up 2 plus 3. 2 plus 3 equals 5. So the cumulative frequency would be 5 numbers are less than 91. For the next class, it's going to be all the numbers before the fourth class starts. So all the numbers less than 102. And what we do is we'd say, well, 2 plus 3 was 5. Now we're going to add 8 to it. So 5 plus 8, 8, 9, 10, 11, 12, 13. The next class are all numbers that are less than 113, because that would be where the fifth class starts. So we're going to take our 2 plus 3 plus 8, and now we're going to do adding 19. So 13 plus 19 would be 32. The next class would be all the numbers falling before 124. So we'll take our 32 and we're going to add 22 to it. That'll give us 54. The next class will be all the numbers falling before 135. So I'm going to take my 54 and I'm going to add 3. And I'll get 57. The last class would be all the numbers. Well, let's see. The very last class here goes from 135 to 145. So all of these numbers fall below 146. So I'm going to say 57 is what I had so far and add 3. And I should get 60. This last number should always be the same as the total amount of items in your frequency distribution. Now that we know how to make a frequency distribution, we can look at the shape of it. So a normal distribution is bell-shaped. So the frequencies will start low, then increase to 1 or 2 high frequencies, and then decrease to a lower frequency again. The distribution is approximately symmetric, with frequencies before the maximum being roughly a mirror image of those that follow the maximum. So a normal distribution, you'll see in the middle here, if we had a line, will go up and then down. Now this is a little bit beyond this chapter, but this middle will be roughly your mean of your data and your mean of your data, and your median will fall in the same place for a normal distribution. Now, are all distributions going to take on that perfect shape? No. We also have skew left and skew right. So for data that skews to the left, you'll have a hump over here, but then you'll have some data values that are a little bit lower than the rest. So in this type, your median of your data, which is your middle value, will be right here. But then think about taking a test. If the whole class takes a test and say like our middle grade on the test was 83%, but then Susie didn't take the test, so she got a 0. What would that 0 do to our class average? Would it keep it at the middle point, the middle grade, or would it bring it up or bring it down? That 0 would bring it down. So for skew left, we're going to find that our mean or average is lower than your median value. Now, we can also have data that skews to the right, meaning most of the data would be down here, but then there's a few data values that are a little bit higher than the rest. So in this case, if our median or middle value, when we line up our data in order, is right here, the mean would be higher. And the mean would be higher if you think about it. Our whole class took a test and say the middle grade on the test when I lined them all up was, a 72%. So if I took all your test grades and put them in order, the middle grade in the pile would be 72%. But say most people did around that area, but then there was one person who got the test right, and then on top of it, she got 10 points bonus. Well, that would certainly, if she got 110, that would drag our test score average up, so the mean is higher than the median for skew right. So let's take a look at our tree circumference frequency distribution, and we'll see if we think it appears normal. So you can see here our frequency distribution. We're going to look at the frequencies that are highlighted in pink, and on either end they're low. But in the middle, they become a little bit higher, and then they taper down again. So this could be relatively normal. You could consider this to be a relatively normal distribution. Is it going to be perfect? No, because real life is usually not perfect. Looking at data, it's good to look at whether it's normal or it skews left or skews right. But another thing you might see when you're looking at a frequency distribution or a histogram is the presence of gaps. Gaps can show that data are from 2 or more different populations. However, the converse is not true. So the reverse of that. Because data from different populations don't have to result in gaps. They could overlap. But here's an example to show you what I mean. We have a frequency distribution of weights of a random sample of pennies. So you can see the weights in grams are on the left, and then we have the frequencies. And we have 18 and then 19 in our first 2 classes, but then we have 3 classes with no data at all. And then we have 3 more classes after that have 2 and then 25 and then 8 pennies in each class. So what's up with that? Why are there, some low weights and then there's no middle weight pennies and then there's a lot of the higher weight pennies? Well, that's a gap in the data. And I don't expect you to know why that gap is there for this particular example, but it's suggesting, if we saw something like this, that maybe our pennies are from two different populations. Now, I'm here to tell you that these pennies actually are from different populations. So before 1983, pennies were made with 95% copper and 5% zinc. And then after 1983, there was a switch up in how they created pennies. So now, after 1983, they're 2.5% copper and 97.5% zinc. So that switch up in how they make the pennies made for a change in weight in grams. Are we going to notice that weight when we're talking about a difference between 2.4 grams and 3.19? To our naked eye and hand, we might not notice that difference, but it is there if you go ahead and weigh pennies before and after that time. So that's an example of gaps in data. Gaps in data might suggest that the data is from 2 different sources. However, if we have data from 2 different sources, we're not necessarily going to see a gap because they could overlap. We can also use frequency distributions to compare data. So we worked with our McDonald's example at the beginning of this section, and looking at the McDonald's example, you can see we have a relative frequency distribution here, just like the one we created before. But also now I've added a column of Dunkin' Donuts information for wait times at the drive-thru. And you can see the Dunkin' Donuts data sits between 25 and 224 seconds, while McDonald's data sits between 75 and 324 seconds. When we're comparing these relative frequencies, we see that there are some major differences. On average, it looks like people are spending less time waiting at Dunkin' Donuts, but there could be some reasonable explanations for that. For example, when people go to Dunkin' Donuts, they're probably grabbing a coffee more likely, and a lot of the Dunkin' Donuts food, there's pastries like donuts, stuff that's ready-made to go. So there's not a lot of preparation involved upon the order. Whereas at McDonald's, if you're getting a burger and fries, it's going to take a minute to get the burger and fries ready. So it's reasonable to expect that you'd be waiting more at McDonald's than at Dunkin' Donuts. Would it be reasonable to use a regular frequency distribution instead of a relative frequency distribution for this comparison? No. When you're comparing 2 different sources, a lot of times it's better to use your relative frequency distribution because, first off, we might not have the same number of data points, and it wouldn't really tell us much if I had, 60 data points from McDonald's and then I had 100 from Dunkin' Donuts. It would be hard to see the numbers in each category next to each other. So showing the percentages gives us, some point of reference where we can compare these 2 data sets. So now you know all about frequency distributions, and we will pick up with histograms and that information that I asked you to put into your calculator on Wednesday. Thanks again for bearing with me through the technical difficulties, and hopefully it'll all be sorted out by next class. I wasn't expecting that. Have a great day. I'll see you on Wednesday.